Hello learners, welcome to this course on Embedded System Design using Raspberry Pi 4. In this tutorial, I will be describing about how to interface sensor with Raspberry Pi 4 module. Sensors are nothing but transducer which takes one form of energy and it converts it to another form. For example, a temperature sensor. It measures the temperature and it gives the output in terms of voltage or current. So by reading this voltage or current, we can estimate what value of temperature is available in the environment. Similarly, we have pressure sensor where we measure the force applied to a pressure sensor and it gets converted into a voltage or current. So we need to read these values to estimate what is the temperature or pressure available in the real-time scenario. And it is very vital in an embedded system application because the actuation or control aspect depends upon this sensor inputs. So we will be describing about how to interface this sensor with Raspberry Pi 4. The complete project and its code will be available in the GitHub repository link given below. A sensor, as I said, it converts one form of energy into another form. So this data from a sensor needs to be processed by the controller. So in order to process this data, we need to have an analog to digital converter. So an analog to digital converter is needed to convert this analog value into a digital value because our controller is going to be a digital device which can process only digital data. In order to do that, we have an IC called as ADC0808 IC which converts your analog input to a 8-bit digital value. So 8-bit represents after conversion process, after converting the analog data, we will get a 8-bit result, 8-bit digital data. We have different ICs for getting 10-bit result, 12-bit result, 16-bit result, etc. So in this tutorial, I am going to talk about one such IC is called as ADC0808 IC, which gives me a 8-bit result after conversion process. So ADCs, analog to digital converters, are available with different mechanism like flash ADCs are available, successive approximation ADCs are available, sigma delta ADCs are available. In this IC, ADC0808 IC, it makes use of successive approximation ADC. So this is the mechanism by which your analog voltage gets converted into a digital value. We will look at how this works, successive approximation ADC. So in this successive approximation ADC, we will be having a register called as successive approximation register, so which holds the digital data. So since my output is going to be a 8-bit result, we have 8 bits of information here, D0 to D7. So D0 represents the LSB bit, least significant bit, and D7 represents the MSB bit, which is your most significant bit. Since I have 8 bits, my values can be varying from 0, 0, 0, 0, 0, 0, 0, 0, 8 zeros. It can go up to 1, 1, 1, 1, 1, 1, 1, 1. So in decimal, we can write it as from 0 to, it can vary up to 255. So this successive approximation ADC contains this register with these values. So when an input voltage, when a sensor voltage needs to be processed, we will provide the input here to the sample and hold circuit. So this sample and hold circuit, it will take the samples. For example, I have a voltage variation which comes continuously with respect to time. X-axis is time and Y-axis is going to be a voltage. So here I have an analog signal where I get voltage for all the time values. In sample and hold circuit, we will try to take the samples from the input signal. Then the samples will be converted into discrete levels using quantization block. After quantization, this discrete levels will be converted into a binary values. So that is how this analog data gets converted into a digital data. So there are three steps. So we have a sample and hold circuit which takes discrete samples from the input signal and it goes into a quantizer. So quantizer converts the discrete samples into discrete levels. Then from the discrete levels it goes into a encoder block which gives the digital bit pattern. So I will get a 8-bit result here which corresponds to the input voltage. So this is how the analog signal is getting converted into a digital value. So here we give the input voltage, it goes into a sample and hold circuit, thereby the samples are selected. Then that particular voltage is compared with the voltage generated by this digital to analog converter. So this digital to analog converter gets the digital data from your successive approximation register. So for example, let us assume I have 8 zeros here. It goes as an input to your DAC. So DAC will convert this digital data into a analog data. It's a reverse process of your ADC. So it will give me a 0 volt here. So this 0 volt will be compared with the input voltage. If it is not matching, in that case the next value, which is 701, will go as an input. And here it will generate 19.6 millivolt as an output. This digital to analog converter we generated 19.6 millivolt as an output. And this will be compared. So like this, one by one the digital data, it goes into this DAC and the voltage will be generated and this voltage will be compared with the input voltage. Whenever there is a match or whenever there is a closest match, in that case the corresponding bit pattern will be obtained and it will come as an output. So that is how this successive approximation ADC is going to work. So one more time, let me explain this. We take an input voltage. So this input voltage goes as an input to your comparator, and the successive approximation register is going to have a values, digital values from 0 to 255. So one by one the values will be taken and it will be given as an input to your DAC, digital to analog converter. So this digital to analog converter will generate a voltage, and this voltage will be compared with this input voltage. Whenever there is a match of this voltage, the comparator will generate a signal and the corresponding bit pattern D0 to D7 will come as an output. So that is how this successive approximation ADC is going to work. And each ADC, it requires a reference voltage. So reference voltage represents how much the input voltage can swing. So for example, if I use a reference voltage of 5 volt, my input voltage can swing between 0 to 5 volt. If my reference voltage is 2.5 volt, then the input voltage can swing between 0 to 2.5 volt. So the reference voltage determines how much the input voltage is going to swing. So this reference voltage can be the IC supply voltage, or we can also provide externally the voltage, or it can be generated internally also. So we have multiple options and we need to configure it. And another important factor is your resolution. So ADC resolution is very, very important. So ADC resolution is nothing but is the smallest voltage change which can be represented as a proper digital bit pattern. For example, I said that if I have a binary data of 8 zeros, then this DAC is going to produce a voltage of 0 volt. And when I have this 701, my DAC is going to produce a voltage of 19.6 millivolt. So this is called as a resolution. This is the smallest voltage change which can be represented as a proper binary bit pattern. If I have a voltage less than 19.6, for example 4.5 millivolt or 7.7 millivolt, In that case, either I have to go with this lower bit pattern or I have to come with a higher bit pattern. So in both cases I have a error. It is not a proper representation, whereas 0 volt is represented properly by this bit pattern. 19.6 millivolt is represented by this proper bit pattern. If I have a 5000 millivolt, which is nothing but your 5 volt, is represented by this proper bit pattern. So this is the smallest voltage change which can be measured using a ADC. So how to calculate this resolution? So resolution is calculated using this formula. Reference voltage divided by 2 power n minus 1, where this n represents whether it is a 8-bit ADC or 10-bit ADC or 12-bit ADC. So here we are going to take ADC 0808 AC. So our n value is 8. So let us consider the reference voltage to be 5 volt. It is represented as a 5000 millivolt. So 5000 millivolt divided by 2 power 8 minus 1, which comes about to be 19.6 millivolt. Which means this is the smallest voltage change which can be measured by this ADC. So the first voltage which we measure is 0 volt, and the next subsequent voltage which can be represented properly in a binary bit pattern is 19.6 millivolt. Again I have to add 19.6 millivolt with 19.6 millivolt, thereby I get this 39.2 millivolt. So this is the next voltage which can be represented properly as a bit pattern. Similarly, 39.2 should be added with 19.6 millivolt, thereby I get the next level. So like this, if I go on, if I take 255 steps, I will reach this 5000 millivolt. Right? So we have from 0 to final value is 255. So I have about 255 steps. Altogether 256 discrete values are there. How many steps I have? I have 255 steps are available. So these are called as quantization steps. So this is the smallest voltage change which can be measured by this ADC 0808. If I want to improve this resolution, in that case what I have to do? If you look at this formula, only two options are available. Either I can vary the reference voltage or I can vary the n. Right? So n is fixed for this ADC 0808, it's a 8-bit ADC. So n is fixed. If I want to change the n value, I have to go with another different IC where my n value will be 10 or 12 or 16. Right? So in that case, if I use a n value to be 10, so what will be the resolution? If I have a reference voltage of 5 volt, so 5 volt divided by 2 power 10 minus 1, then the resolution is 4.88 millivolt. In that case, this 8 zeros is nothing but 0 volt. The next level will be 4.88 millivolt. And the next level will be, again I have to add 4.88, which will be your 9.6 millivolt. So that is how we can change the resolution. Here you can see the smallest voltage change which can be represented is 4.88. That is why we call it as a resolution of a ADC. Another option is by changing the reference voltage. So instead of using 5 volt as a reference voltage, I can change it to a 2.5 volt, which is 2500 millivolt. In that case also, the smallest voltage change which can be measured gets improved. Even 9.8 millivolt variation can be measured properly. So this resolution plays a very, very vital role in ADC. So the applications where we can use this ADCs or sensor measurement is temperature based home automation, industrial process automation, etc. Numerous applications are available. Here I show a typical ADC 0808 IC. I will describe these pins in the subsequent slides. So here we can simulate this ADC alone in a Proteus 8.13 professional software. So we take a ADC 0808 IC, which is a 8-bit ADC. 8-bit ADC. So we need to provide the input, right? So I have 8 channels to give the inputs, IN0 to IN7. So I can connect up to 8 sensors to this IC, but remember, only one sensor data can be converted at a particular time. Right. So I can't convert all the data in parallel, right? So only one sensor data can be converted at a particular time instant. But I can connect 8 sensors. Each sensor can be connected to this IN0, IN1, IN2 up to IN7. So here I have taken a potentiometer, right? So anyway, a sensor, what it is going to give? It is going to give a corresponding voltage or current variation. So I am connecting a potentiometer as an equivalent. So by varying this potentiometer value, the voltage given to this IN0 is going to get varied. And in order to select these channels, in order to select a sensor, we have address lines, address A, B and C. So if I put 0, 0, 0 here, then IN0 will be selected. If I put 0, 0, 1, then IN1 will be selected. If I put 1, 1, 1, in that case IN7 will be selected. So these address lines are used to select a particular input. We can connect 8 inputs, but I should say which input I should convert. That is done with the help of this address A, address B and address C. So by providing proper bit pattern to this address, we can select a particular input for conversion process. And in order to indicate this A, B and C as an address, we make use of this ALE signal. So ALE signal stands for address latch enable. So if I give 1 to this ALE, then this ABC will be considered as an address and the corresponding input will be selected. Then we give the reference voltage for this ADC here, right? So here I am going to use the supply voltage. Okay, 5 volt supply voltage, I am going to use it as a reference voltage. So it is connected here. V reference plus is connected to 5 volt, V reference minus is connected to ground. Then we have a clock signal. A clock signal is required for this A to D conversion process. So since I have a 8-bit ADC here, it will approximately take 10 clock cycles to convert the input data. It requires minimum 10 clock cycles to get converted into a digital data. So we have to provide a clock signal. So here we try to provide a clock signal of about 500 kilohertz. So this determines the speed of conversion process. If I use a low frequency clock, then the speed of conversion will be slow. If I use a high frequency clock, the speed of conversion will be high. Then we have a start signal. So once I want a data to be converted, right? So as a user, we should provide this start signal. So this start signal will be a high to low pulse. Whenever I provide a high to low pulse, the conversion will get initiated. And after conversion process, the end of conversion signal will be generated by the ADC. So start the conversion process should be provided by the user. User should provide this signal. Okay, user should give, you start the process. Once the 8-bit data is ready after the conversion process, the ADC will give a signal called as EOC, end of conversion. End of conversion signal. Once end of conversion signal is obtained, there will be a register inside. In that register, we will have the output data. So this data should come as an output here, out1 to out8. So in order to get this register data to the pins, we make use of this line called as output enable. If I put output enable to be 1, in that case, the register data will come as an output through this out1 to out8. This out1 will be a MSB data and out8 will be a LSB data. For example, if I take 1111, 0010, some 8-bit pattern. So this bit is your LSB data and this bit is your MSB data. LSB stands for least significant bit, MSB stands for most significant bit. So here you can see that this 0 will come in your LSB position and this one will come in your MSB position. So we can connect a LED array there to see the output. For example, here we set some voltage through this potentiometer. So and I measure that voltage using a voltage probe. It shows something like a 3.14 volt. You can see a binary bit pattern here. Okay, so this binary bit pattern is nothing but this value 101 00001. So if I convert this value, so this is for 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5. So this is 2 power 5, 2 power 6 and 2 power 7. So if I take this value, 2 power 7 is 128, 2 power 5 is 32 and 2 power 0 is 1. So if I add all these values, I will get 161. So if I get this binary bit pattern, this is the corresponding decimal value. So I want to know the voltage. To know the voltage, what we do? We take this digital value 161, multiply with the resolution of your ADC. So this is the resolution of my ADC. So when I do that, I get this 3.15 volt. So this is the voltage which we apply here. So we have converted our analog data into a digital data. So this is the analog data and it gets converted into digital data, and we are displaying the digital data using a LED array. Same way, if I have this, all these LEDs to be 1, in that case my decimal value is 255. So I can multiply this 255 with the resolution of the ADC, thereby I get a 5 volt. So depending upon the digital data, we can estimate what is the voltage given to a particular input in the ADC. Now let us look at how to interface this sensor data with your Raspberry Pi 4 module. So here we are going to use Proteus 8.13 professional software for simulation part, and the language of programming is going to be Python. We don't have a ADC inbuilt in our Raspberry Pi 4 module, so we have to make use of this ADC as an external component. So we take a Raspberry Pi 4 module and we are going to connect ADC 0808, which is a 8-bit ADC, to this Raspberry Pi 4. And our sensor data will be connected to this ADC 0808 IC. So we are going to use IN0 channel. So I already have said that we have 8 channels, IN0 to IN7. I am going to connect the sensor data to IN0 and I have to select this channel. For selecting the channels, I have to use this address lines ABC. So and I am going to set it with 000, which means IN0 will be selected. And to indicate this as an address, we make use of a ALE signal. So ALE signal, we will provide a high to low pulse. So high will indicate this as an address. Then we have other control lines like start off conversion. So this start off conversion also should be a high to low pulse. When I provide this signal, the conversion will start. Once the conversion is complete, end of conversion signal will be generated. So this signal we have to read using your Raspberry Pi 4 module. So upon reading this, we have to set a output enable signal from your Raspberry Pi 4 module. So output enable, so thereby the result in the register will come as an output. Then we are going to read this signal from this ADC via Raspberry Pi 4 module. So reading is going to happen using this GPIO pins from GPIO 5, GPIO 6, GPIO 12, 13, 16, 19, 20, 26. And 5 will be used as a MSB bit and the GPIO 26 will be used as a LSB bit. So we are going to read this data. After reading this data, I am going to send this data to an LED. LED is connected to this 8 pins, 25, 24, 23, 22, 27, 18, 17 and 4. And we try to display that value in the LED. So where the 25 will contain the MSB bit and GPIO 4 will contain the LSB bit. So we take the sensor data, read it, convert it and send the data to your Raspberry Pi. So Raspberry Pi is going to read that 8-bit data and it is going to send that 8-bit data to a LED for display. So that is what we are going to do in this project. So this is a complete circuit where we can see we have a Raspberry Pi 4 module here and I have taken ADC 0808 IC here. And I have connected a potentiometer which can be varied and it is connected to IN0. To select this channel, I have set this ABC to be in ground, which means 0, 0, 0. And in order to say this as an address, we will generate the ALE signal through your Raspberry Pi 4. So here ALE signal will be high to low signal, that I will try to show it in the code. And we connect a reference voltage of 5 volt here. So our input voltage can swing between 0 to 5 volt. Then we have a clock source. So the clock source I have connected to be 500 kilohertz clock source. Then we have a start signal which is connected to this GPIO 21 pin. So here also we will generate a high to low pulse, thereby the conversion will start. So once the conversion is complete, this EOC signal will be generated. And this will go as an input to the Raspberry Pi using the GPIO 7 pin. Upon reading this EOC signal, output enabled signal will be generated through this GPIO 3. Then the register data, it comes as an output to your out1 to out8 signal, and this data will be read using this GPIO pins. Upon reading this, we will send the data, 8-bit data, through this GPIO 4 to 17 connected to your LED array. And the converted result appears on the LED array. So here you can see here, I have 0, 1, 1, 1, 1, 1, 1, 1. So this is the binary bit pattern after converted value. So when I want to know the voltage, we take this binary bit pattern, convert it into decimal, which is nothing but 127, multiply it with the resolution of your ADC, 19.6 millivolt, it comes about to be 2489 millivolt, which is nothing but your 2.5 volt. So that is the voltage which you have applied here. If 50% represents 2.5 volt. 100% represents 5 volt. 0% represents 0 volt. So we give an input voltage of 2.5 volt. That 2.5 volt is represented as a binary bit pattern here. Now let us look at the coding part. So in order to use the GPIO lines, we make use of RPI.GPIO package. Then in order to introduce delay function, we make use of the time package. Then from ADC 0808, I have to get this data into your Raspberry Pi, right? So this data, output data should come as an input to your Raspberry Pi. So that is this ADC underscore data pins. So these are the GPIO pins, where 26 represents the LSB bit and 5 represents the MSB bit. Same way we will be connecting the output of the Raspberry Pi to the LED array. We will be connecting it to the LED array. So for that I initialize the LED pins. So the LED pins are 4 to 25. So where the 4 represents again LSB and 25 represents MSB. Then we have other control lines like ALE is connected to GPIO 2, start signal is connected to GPIO 21, end of conversion signal is connected to GPIO 7, and output enable is connected to GPIO 3. So first we say that I am going to use the IC pin configuration. So BCM stands for Broadcom IC. So we have BCM 2711 IC, which is a ARM Cortex A72 processor, which is available in your Raspberry Pi 4 module. So I am going to say that we are going to use a pin of ICs. Then I am going to set the data direction for the GPIO pins. So ADC underscore data pins will be an input to your Raspberry Pi. So we configure it as an GPIO.in. Whereas ALE, start and output enable are output signals from the Raspberry Pi. So we configure it as GPIO.out. And end of conversion will be an input to the Raspberry Pi. So we configure it as GPIO.in. Then LED pins are output pins from the Raspberry Pi. So we take one by one the pin and configure it as output pins. So the data direction is set here. Next, we define a function for reading the ADC value. As I said, to read an ADC value, first thing is I have to make this ALE to be an high to low pulse. Then once I make this high to low pulse, then ABC, which I give as 000, will be treated as an address. and input voltage IN0 will be selected. Next thing is I have to generate this start signal. So start signal also should be an I2 low pulse. So that is provided here. So first GPIO.output ALE is set to 1 and this 1 will be retained for 1 millisecond. Then I am going to give the start signal again high and this will be retained for 1 millisecond. After this we make the ALE to be 0, which means I have ALE high to low pulse. Same way start signal also goes to 0, so I have a high to low pulse here. So once conversion is started, we are waiting for the end of conversion signal. Once the conversion is complete, end of conversion signal will be generated. So once this input is changed to 1, I need to read the result. Now the result is available, I need to read it. So what we do is we set the output enabled signal to be 1. So once the output enabled signal is set, the internal register result will come as an output through the pins. Right? So I am going to read that pin values. So we are going to take bit pin by pin and we are going to read the values. So I am going to take first the LSB pin. Okay, initially the value is 0. So value is 0 in the sense it is nothing but 0, 0, 0, 0, 0, 0, 0, 0. Right? So now first pin I am going to read. I am going to read the first pin. Okay, the first pin will be your LSB pin. Right? When I read, for example, my value is 1. In that case, I have to put value here. Okay, value should be changed from 0 to 1. Right? So how I am going to do this? I am going to read this LSB position. Right? If it is 1, if the input is 1, in that case what I do? I take 1 left shift by 0. Right? So 1 I am going to do left shift by 0 times. When the for loop runs for the first time, I value will be 0. Right? So which means I am going to OR this value with the original value. So my original value is 0, 0, 0, 0, 0, 0, 0, 0. So now I am going to take 1 and I am going to do OR operation. Then my value will be 0, 0, 0, 0, 0, 0, 0, 1. So this will come as an output in my value. When the for loop runs for the second time, okay, let me one more time, let me put it. So value, initially it was 0, 0, 0, 0, 0, 0, 0, 0, right? So that we have set here. So I am reading the first pin. When the for loop runs for the first time, I value will be 0, right? So I am going to read that value. So which means if the input for that pin is 1, in that case this condition is satisfied. So I have to do this operation. So here what I do, I take 1 left shift by I value 0. So 0 means no shift. So I have 1 here. So my result will be 1, 0, 0, 0, 0, 0, 0, 0. When the for loop runs for the second time, right, now I is changed to 1. Again I read the next input pin, right, second input pin. So if that second input pin is also 1, in that case what will happen? 1, I have to do left shift by 1 time because my I value is now 1, right. So which means what happens? Left shift, 1 is left shift. So 1 means it is nothing but 0, 0, 0, 0, 0, 0, 0, 1, right. So this is 1. I am going to do a left shift by 1 time. So this bit will come here. So I will get 0, 0, 0, 0, 0, 0, 1, 0, right. So this value I need to add it here, not add OR operation I have to perform. So I take this value 0, 0, 0, 0, 0, 0, 1, 0. So we are going to do OR operation. So when I do OR operation, I will get 0, 0, 0, 0, 0, 0, 1, 1. So now the second bit data I have inserted. Same way, third bit data, fourth bit data, fifth bit data. So like that we are going to append. So after I value changes from 0 to 7, once it completes, I will get all the 8-bit values here. Once it is done, we set the output enable line to be 0. Right. So this function reads the ADC data from your ADC 0808 IC. So here what we do, the simple operation is we set the ALE to be high to low pulse, start signal to be high to low pulse, then wait for EOC. Once EOC is obtained, we set output enable to be high. Then read the value. So reading the value, I am going to take it from the LSB pin, right? First LSB pin value is read. Then next bit. Then next bit. Finally, I will read the MSB pin value. After reading all this 8-bit data, we are setting the output enable to be 0. Right? So this is the process by which we are going to read the ADC value. Then to display it again, pin by pin I have to display the value. We write a function called as display underscore LED. We take one by one the pin. So now value, for example, let us assume I have the 8-bit value to be 11110101. Some 8-bit value is there, right? So I am going to take one by one. So this value I should send it to the LED which represents LSB bit. Next value to the next LED, next value to the next LED. So this final value to the LED which represents MSB bit, right? So I have to take one by one and I have to send it. So we take this value, do right shift by I times. So this I will vary from 0 to 7. Right? So for example, when the for loop runs for the first time, I value will be 0. Right? In that case, value is this value. Right? So this is your value. What we do here? Right shift by 0. Right? Right shift by 0 means no shift. We take this data as it is and do AND with 1. So when I do AND with 1, so I get this bit. So this value is coming here. Right? And this value I am going to send it to the pin. When the for loop runs for the second time, now I value will be 1. Right? When the I value is 1, what we do? We take this value, so value is 11110101, right? This value I am going to do a right shift by 1 time. So when I do right shift by 1 time, what happens? It becomes 01111010. So now this bit, the second bit comes here. Now this I am going to do it AND with 1. So I get this bit and send it to this next pin. So like this we are going to pick each signal and we are going to send it to the corresponding pin. So thereby the LEDs connected to this pins will display the digital data. Then we write a main function. So in a main function, our system should run continuously. So we make use of a while loop and the condition is always true. In that I am going to call this function called as read ADC. So when I call this ADC, this function will be called and the final converted result value will appear here, ADC underscore value. So this value I am going to print and see. Then I am going to move this data to a LED, right? So I am going to call this display LED function. So thereby the LEDs will display the values. Then I wait for 1 second, then I clean up the signal. So that is how this main function is defined. Now we call this program using this main program and we will try to see. Now let us execute and let us look at the output. So here we use Proteus 8.13 professional software. I described this circuit. We make use of a Raspberry Pi 4 connected to a ADC 0808 IC and I'm going to use the sensor as a potentiometer. And this potentiometer can be varied, and we give the input signal to this IN0. And corresponding address lines have been set, reference voltage have been set, clock signal has been set, and we take the data from the ADC 0808, give us an input to your Raspberry Pi 4. Then this Raspberry Pi 4 is going to send the result to this LED array. Then we have a source code here. So in source code, the program which I explained is available here. We import the packages, set the pins, set the data direction for the pins, and then we are going to read the ADC value through this function. Then we try to display the value through this function. Then we have a main program where we call this read ADC, display the value, then display the LED. Display the value in the LED, then we call the main program. We execute this program, then go to this schematic capture and execute the program. So here you can see right now the voltage is 50%, which means our reference voltage is 5 volt. So 50% of 5 volt is nothing but 2.5 volt. So we get this digital bit pattern. Now when I start increasing this value, you can see the corresponding bit pattern changes. Right? So as I start increasing the value, the corresponding digital data, which you can see here, it gets changing. For 60%, this is the bit pattern. 60% of 5 volt. You will get this bit pattern. Same way I can increase or decrease. Thereby you can see a change in our digital data which we generate. So this is how a sensor data can be read using your Raspberry Pi 4 module, and we can display the output in your LED arrays. So in this tutorial I discussed about how to interface a ADC 0808 module with Raspberry Pi 4, because we don't have an inbuilt ADC here, right? So I have to connect it externally. So after conversion process, we read the data using a Raspberry Pi 4 and try to display the output in your LED. Thanks for watching. Please like and subscribe for more technical learning. The complete code and simulation of the project is available in the GitHub repository link given below. Thank you.